Yes. Spring 2015. Okay, spring 2015. Exam 1, number 8. Just a second while I get there. This is page 12, and you want to have to do this because we skipped crystal structures. Yes, this is crystal structures.
Wait, can you do it?
You can ask me later, but I won't do it now because we're exam focused. I would love to cover it, but I cannot. Number 2. Hexagonal crystal structures are crystal structures. Yes, we are not covering that. I apologize. I would love to cover it. Number 2. 3. I'm coming back to 3. Number 4. Where are you? Yes. What page? 52? Whoa. Sounds old. Page 52, what number? Part B of number 21. Okay? Spring 2006, exam 1. This problem right here, page 52. Part B though. Okay, let's read this. Boron and oxygen are put in a closed container, allowed to react. So much water according to this reaction, which is this one, right? Number 1? Yeah, reaction 1, there we go. Because the close is in contact with the water, water temperature rises and boils. Does not go above 100. What's the heat capacity calorimeter? Okay, so calorimeter, sum of the Q's equals 0. So you're going to go and let me draw what's going on. In here, in your container with water is a reaction. The reaction listed. This is hot. You know that because it says so and it's negative. It's hot, makes the water warm up to boiling, but it says it doesn't go above boiling. So the water continues to boil but doesn't disappear fully. Okay? So, some of the cues. So let's see, first, what changes temperature? I bet the water does. The calorimeter. I think that's it. There's one more cue though. Yeah, cue reaction. Is that okay for a setup? Okay, so now, these, well, let's do each one separately. So, and I'll let you solve it if that's okay. Did I miss a cue? Oh yeah, thanks. Nice. And the foils. Excellent. Genius. QW mCp delta T. The mass of the water. Now the mass of the water is not given, so you got to go density times volume. CP on the back of the exam. Is it okay if I leave delta T to you? Okay. This, they want to know the heat capacity calorimeter, so that's question mark. Delta T I'll leave to you if that's okay. Okay. Q of reaction, that's given in the problem itself. They give you the delta H. That's cool? Okay. Q of boiling, that we call delta H of vaporization. That's on the back of the test. You'll need to multiply that by N because it'll be per mole. There's only one unknown and that's C. Does that feel okay? Okay, you were number 4, right? Did I miss something? N. Oh yeah, what's N? First, what does N stand for? Moles. So you need to find moles of the water. Is that okay? Okay. Can I go back to 3 now? Are you ready? Okay. Yes. Yes. Okay. I don't know other classes if you covered this. If not, you'll have to bear with me. Let's say I have 1 molar NaOH and I have 1 molar strontium hydroxide. These are both bases. If you want to change to normality, this has 1 equivalent of OH, so this would be 1 normal. This has 2 OHs, so it would be 2 times 1, or 2 normal. That's it. So it's the number of OHs. Is that cool? Okay. 5. Oh, also.
That's the same question.
Oh, this is beautiful. Okay. 6. Do you have a page number for me? Oh. Odd. Spring 2009. 7, you said?
Yeah.
This one? Look familiar? Okay. All right. Class A has a volume of this and contains that many grams of volatile liquid. Class B, same liquid, both classes are closed, both are at the same temperature. What's the ratio of the vapor pressure? How do you do this? What math equation am I going to use? I will not use the math equation. Okay, so now what? It's even easier. Is it the same liquid? Same temperature? Same vapor pressure? Done. The vapor pressure is proportional to the temperature. That's it. Remember when I showed you, let me get to this graph here. Vapor pressure is proportional to the temperature. That's all you need to know. I'll find it. Here we go. Remember this, page 23? Vapor pressure is proportional to the temperature. Done. Doesn't matter how much there is. It's not proportional to the moles. The temperature. All right. That was 6, I think. 7? Yes. Well, one at a time. So 44, number 1. Page 44, number 1. All right, this one. Okay, this is winter 2007, number 44. On the phase diagram of CO. Kind of hard to see, but that's solid liquid gas, which is false. At 5.11 and minus 56, there's 3 phases. Is that true?
Yes.
Yeah, that's a triple point. Solid form is denser than the liquid form. Is that true?
Yeah.
Usually, CO2 is a gas at 74 atmospheres, well, way up here, and 32. Is that true? No, what would it be? Supercritical fluid. That doesn't look good. 5.11 and 56. It's a solid. 5.1. That's more like a triple point. And at 70, increasing the temperature. Oh my gosh. 70 here. Increasing the temperature from minus 56 about here to 25 here, well, from the solid to liquid. That happened, right? Okay, so we think it's C or D? What did I say? Now I forgot. Which ones did I say were wrong? Did I say B? Okay. Whatever I said, it's easy. You can just look here. I guess I said C, I hope. See which one was that about? Yeah, that's a supercritical fluid. That doesn't look good. Oh, this is 56 56, so it's a little to the left. Okay, so C looks like the worst one. Is that okay? All right. Anybody else have questions? We'll restart. 1, 2, 3, 4. Okay, 1. Where'd you go? Did you want to get in on this too? You said you had other questions. You want to be 5? Okay, 1. A question about delta H of solution, just in general. These two are always what? Endo or exo? And this one is always exo. So that's always true. We are not going to do any calculations, but delta H of solution could be thus endo or exothermic. Could feel cold or feel hot. A solution will form when delta H of solution is a generally small number close to 0. Okay. It may or may not form in other scenarios though. So it's all conceptual. The main concept, like dissolves like. Okay? 2. Where did you go? Way up there, yes. 29. Okay. And hold up just a minute. 29. You said 19? Oh yeah, this is a fun one. Okay, this is this question, right? The Hess law. Alright, I didn't give you one equation. First of all, so I didn't give you the delta H. This is a little bit backwards. Usually you find this delta H. This time you're going to find that one. That's the cool part. But how are you going to figure out, anybody, what this reaction is? How do you know what you need the reaction? It cannot be derived, per se. Okay, I would recommend reading the question. Combustion reaction. Cool. What is the only thing that will combust here, most likely? Yeah, and you don't see it here or here, so it has to be here. So, combustion of C2H6, let's write that down. I guess I'll try this. So yes, you have to know your combustion reaction. Now balance it. 2, 2, 6, so 3, 4, 5, 6, 7, 7 halves. So far okay? I got it literally because it said combustion reaction there, and that's the only thing that could combust. Do you want me to, was that the hard part, or do you want me to go on and do the numbers? You feel okay now? Yeah, that was the hard part for most students. Okay, you were 2, is that right? 2, 3. Oh yeah, right behind, yes.
Page 37.
37. 16. Are you in my class? You don't have to be, it's fine. We are not having osmotic pressure, so can you ask me afterwards on this?
Figure it is 17.
17, okay. You mean this stuff? Okay. So let's do 17. Hydrogen peroxide, kind of similar to before, but now you're given a percent mass. Okay, so now you got to go through that action. Let's do that. Okay, so we have, you got to go backwards for percent mass. That means 3 grams of H2O2 for every 100 grams of solution. Is that all right? Just going one step backwards for percent mass. So, because this is in mass, and notice the density of solution of pure water if we need it. So the density of solution, 1 gram per milliliter. All right, so I've got the mass of H2O2. That's 3. I've got the mass of solution. That's 100. The mass of water would be what? Remember, the masses you can add and subtract. So 100 minus 3, 97. So the solution plus the solvent, water, equals 100. Okay, so now we need to convert these all to moles. Let's do a different color. So I'll set it up for you. I don't have all the numbers. I'll let you do the math. But what you're going to do is find the molar mass of this. 2 oxygens. This should be 34 point something grams per mole. This will give you the moles of H2O2. And then this one, it's 18.02 grams per mole. Now you get the moles of water. And then I will also need of the solution the volume. So let's change the solution to a volume. I'm going to do that by using what? Oh, just the solution density. Gram per milliliter. That'll be 100 milliliters. You'll also want to change this to kilograms, getting ready for the molality solving. Okay, now is there a particular concentration you'd like me to set up? Again, I don't have the numbers for you. There was molarity, molality, mass per volume, etc. Is one of them your favorite, or couple favorites you'd like? You get to choose because you asked the question.
Mass per volume.
Mass per volume. Percent, that would be the mass of the solute in grams. That's 3. Divided by the milliliters of solution. Times 100%. It looks like it's going to be about 3%. Anything? You want to do another one?
Apparently
Oh, did I miscalculate? I could have. You got 30 here?
Can you answer
Did I do the 100 right? Did I do everything other calculations right? That's curious. I don't have that for you. Okay, any other? It could be 3. 3 kind of makes sense to me right now. Hey, there's mistakes. You can correct it for extra credit if you want to. Now you're good? Okay, what number were you? 4. Yes. 54. Sorry, I just want to go fast so I kind of get everybody in here. And we finish before we're kicked out. What number? 9, right here. Okay. Binary liquid is formed by equal number of moles of liquid A and B. So this, you want to ask me how we're going to do Raoult's law? That'll be... Yeah, we'll get to it. It's coming for the exam. Yeah. You're 4. 5? Yeah. Number 12. Page 32. 32. Number 12. This one. Bomb calorimeter. Yeah. Okay. French fries. 0 by 5 to 1. Assume the color has the speed of water. Okay. I can't do both at the same, so it's page 32, string 11, number 12. Got a bottom calorimeter, so you know Q reaction is minus Q cal C delta T. This one, however, also has fries in there, so measure the calories of fries. Oh yeah, it's a combustion of fries, okay? We know delta T is 54 minus 22. That's given in the problem. So 32. C, the calorimeter has the same specific heat of water. So we're actually, this happens sometimes when the calorimeter usually is just specific heat or heat capacity, capital C, but sometimes they'll say that it has the same as water. And in that case, when they don't give you capital C, but they say it's the same as water, you'll have to use an MCP delta T in that case. So let me kind of change this line a little bit here. This right there, this right there, you'll have to use the MCP because they say they use the same as water. So MCP for that capital C is equal to the mass of water. You're not given that, but you know it's 5 liters. So I'm going to use the volume times the density, 1 gram per milliliter. And I need to convert the volume units, 1,000 milliliters per liter. So all that just to get the mass, times, I'll have to do this on the next line, the specific heat of water, 44184. Oh, do they want calories or they want calories? 1 calorie per gram degrees C. Okay, so there's that whole term. Let's see if I'm missing anything. Okay, I think that's it. So then to calculate this, that'll be Q reaction, okay? That'll be Q reaction for 22 grams of fries. And then you'll need to, and then you'll want it in calories. So yeah, I'll leave the math to you if that's okay.